Welcome back to Science Uncovered, everyone. Today, we're diving into the fascinating world of materials science, specifically, how we can use powerful new tools to design better catalysts for a greener future. Joining me are Geraint, Matthew, and Kimberly, experts in their fields.
Thanks for having me, Sally. It's exciting to discuss this research. It really bridges the gap between theoretical chemistry and practical applications.
Absolutely. The sheer volume of possibilities in materials science is daunting. We need innovative ways to explore the landscape efficiently.
And that's where this new research comes in. It focuses on using something called graph neural networks to predict electron densities in materials.
Electron densities? That sounds complicated. Can you explain what that means, Kimberly?
Sure. Think of electron density as a map showing where electrons are most likely to be found around atoms in a material. It's fundamental to understanding how atoms interact and behave, and ultimately, how a material will behave. Traditional methods for calculating this are computationally expensive, really slow.
Exactly. And that's where graph neural networks come in. These networks are a type of machine learning that can learn complex patterns from data. They're particularly well suited for representing the relationships between atoms in a material, essentially treating it as a graph.
So, they can learn from a set of known data, and then predict electron density in new, unseen materials. This allows scientists to explore many more possibilities without running laborious experiments or simulations for each material.
So, instead of spending years calculating electron densities, the graph neural networks could do it in a much shorter time frame? That's amazing.
Exactly. The research found that the new method was significantly more accurate than traditional methods, especially when it was trained on large datasets. The larger the dataset, the better it gets at making accurate predictions.
This is really important because electron density is not just an abstract concept. Once you know the electron density, you can predict other properties, like atomic charges and dipole moments, both crucial for understanding a material's behavior.
And these properties are critical for developing new catalysts. For example, in green technologies like water oxidation or carbon dioxide reduction, we need catalysts that are both highly efficient and cost-effective. This approach could significantly accelerate the discovery of these materials.
It sounds like a game changer. But are there any limitations to this approach?
Certainly. The accuracy of the model is directly related to the size and quality of the training data. We need extremely large datasets to get highly precise predictions, and getting that data can be challenging. Also, the model might not be as accurate for predicting entirely new types of materials or complex systems we haven't seen before.
Exactly. And while the method greatly speeds up calculations, it doesn't entirely replace traditional methods. For very precise predictions or systems, we'll likely still rely on more established, albeit slower techniques.
Another challenge lies in actually running these calculations. They are still computationally intensive, even with this acceleration. But the potential benefits for materials discovery far outweigh these limitations.
So, to summarize, this new research shows how graph neural networks can accurately predict electron densities in materials, significantly accelerating the design and discovery of new catalysts, especially for sustainable energy technologies. The more data we feed into it, the more accurate it becomes. While there are limitations, the potential implications are huge.
It's a compelling combination of advanced machine learning and established physical chemistry principles. It offers a more efficient and accurate pathway for designing novel materials.
And that's critical for pushing the boundaries of green technology. We need these tools to explore the vast possibilities for improved catalysts.
Absolutely, and I think we're only scratching the surface of what's possible. The potential applications extend far beyond just catalysts, influencing the design of many materials for various uses.
That's a fantastic overview, everyone. Thank you for joining me on Science Uncovered today. Join us next time when we discuss